Alright, now that we've introduced some of the basics of weather radar, let's dive into an overview of the data that radars output. Perhaps the most widely recognized radar product is reflectivity, which is the amount of energy that returns to the radar after scattering back from a target. Reflectivity tells us where precipitation is occurring and how intense that precipitation is, and it's measured in decibels, or dBz, where z is the meteorological variable for reflectivity. In general, the higher the reflectivity, the heavier the precipitation. Reflectivity values below 40 dBz typically indicate light precipitation, while values above 60 to 65 dBz generally represent extremely heavy precipitation, sometimes including hail. These guidelines can vary based on the size of the raindrops. Small drop sizes, like those in tropical systems, return less energy to the radar and, therefore, yield lower reflectivity values than the larger drops of a typical thunderstorm, despite equally torrential rainfall. As we discussed earlier, Doppler radars also measure the phase shift between an emitted pulse and the energy scattered back to the radar to estimate velocity. A target's velocity is comprised of the speed and direction of the target. Negative velocities, which are illustrated as greens, blues, and pinks on typical radar programs, represent targets that are moving toward the radar. These are also called inbound velocities. On the other hand, positive velocities, your reds, oranges, and browns, represent targets that are moving away from the radar. These are outbound velocities. Velocities near zero show up as gray. Depending on the radar program you're using, velocity is measured in either knots or miles per hour. Typically, higher velocity values indicate targets moving more quickly, but, as we mentioned earlier, this depends on the radar's maximum unambiguous velocity. Again, we'll get into this in depth later on in this module. The velocity of a target that you see on a radar program will almost always be slightly less than the actual velocity of the target because radars are at fixed locations, meaning that they can only measure how fast a target is moving toward or away from the radar itself. This is called radial velocity. Every azimuth angle, which is the radar beam's angle from due north, is associated with a radial. Radial velocity is equal to the actual velocity of the target only when the target's motion is directly toward or away from the radar. In other words, directly along a radial. Therefore, the greater the angle between the radar beam and the target's motion, the less the portion of the target's actual velocity that will be sampled, and the less the radial velocity will be. If a target is moving perfectly perpendicular to the radar beam, its radial velocity will be zero. In addition, standard radial velocity, which I'll refer to as just velocity or base velocity from here on out, is the target's velocity relative to the ground. However, storms and their small-scale phenomena, like tornadoes, move with respect to the ground, which can make it difficult to obtain proper velocity measurements. For example, if a storm has 40 mile per hour winds and is moving directly at the radar at 30 miles per hour, the radar will output an erroneous base velocity of 70 miles per hour. To combat this, we can use a product called storm relative velocity, which subtracts out the storm motion. This can make it much easier to discern areas of rotation within the broader wind field.
Storm chasing is hard. Get expert help from a live coach. Discord community link in description.
Reflectivity and velocity are the two foundational products of weather radar and can tell us a number of things about a storm's behavior and characteristics. However, they only give us a two-dimensional look at targets. Before the early 2010s, WSR-88D radars could only produce reflectivity and velocity measurements, but starting in 2012, the entire network was upgraded to have dual-polarization capabilities. Let me explain. The pulses of energy emitted by a radar oscillate in a specific plane, much like the ripples in a calm pond after you toss a pebble into the water. The orientation of the waves is a property called polarization. Prior to the upgrade, radars could only send out pulses that were oriented horizontally, in other words, horizontally polarized. Today, WSR-88D radars send out pulses that are polarized in both the horizontal and vertical, which allows us to obtain vital information about the size, shape, and orientation of targets rather than just their intensity and velocity. Dual polarization yields a few additional products that can be extremely helpful, especially in severe weather situations. The first is called correlation coefficient, shortened to CC or RhoHV. Correlation coefficient compares the consistency between backscattered power in the horizontal and vertical planes. In simple terms, it tells us how similar or correlated the targets are that the radar samples. Correlation coefficient is unitless and ranges from 0 to 1. If targets have similar shapes and sizes, the correlation coefficient will be close to 1, but if their shapes and sizes are quite varied, correlation coefficient will decrease. For example, if a storm or a portion of a storm consists of only raindrops, the associated correlation coefficient will be near 1, as all the targets are quite similar to one another. However, if a storm consists of a mix of raindrops and large hail, the correlation coefficient may decrease given reduced consistency among the targets. Correlation coefficient is also a good discriminator between meteorological and non-meteorological targets, with most non-meteorological targets registering a CC value below 0.9. The exception is large wet hail and large wet snowflakes, which typically yield CC values between 0.8 and 0.97. The next dual polarization product of note is differential reflectivity, or ZDR, which is essentially the ratio of the backscattered energy in the horizontal plane to the backscattered energy in the vertical plane. After a bit of mathematical cleanup, we get a range of possible ZDR values between positive and negative 7.9 decibels. Differential reflectivity gives us valuable insight into the orientation of targets being sampled. ZDR values near 0 mean that the backscattered energy was similar between the horizontal and vertical planes, indicating more spherical targets like small raindrops or hail. Highly positive ZDR values suggest that targets are much wider than they are tall, such as large raindrops that flatten out as they fall. The opposite is true for highly negative ZDR values. They indicate targets that are much taller than they are wide, such as falling ice crystals or elongated snowflakes. Highly negative ZDR values are quite rare in severe weather situations. The final dual polarization product we'll discuss is specific differential phase, or KDP. KDP is derived from a similar product called differential phase shift, or FDP. In essence, FDP is a measure of attenuation in the horizontal and vertical planes. It can be a bit cumbersome to analyze, so KDP is much more commonly used instead. KDP shows the gradient of FDP, in other words, how phase shift and, in turn, attenuation changes in the horizontal and vertical over a given distance along a radial. Since phase shift is measured in degrees, KDP has units of degrees per kilometer and ranges from -2 to 10. Increasing values of KDP represent an increase in the size and concentration of raindrops, which can attenuate the radar beam more. This suggests heavier rainfall. KDP may vary between areas of precipitation, even if reflectivity among these areas is similar.
Remember to check out those links in the description below, and then watch another video.